All right, this is the second part of the Chapter 5 lecture broadcasts. This is going to be on testing two means, on statistical significance tests for the difference between two sample means. In general, I'm not going to get into the details of how to do each different kind of test. Okay, that was weird. Too much light from outside, I don't know. Anyway, let's get started, okay? Let's just start desktop sharing. So there are a lot of situations where we want to know the difference between two means. We want to know average differences between two groups, for instance. So for instance, who has higher average IQ, people from one college or people from another college? Were there more symptoms for this group of patients before or after a drug was administered to them? Whose mom makes the best cake? You might take a lot of cakes and take the average. On average, whose mom makes the best cake? Which brand of who knows what is more durable? Actually, statistical tests like this are used quite a lot in quality control applications like this. Whose data is stronger? Have them do a bunch of different trials, feats of strength. Are student ACT math scores or reading scores higher? Which one is the higher score? So these all imply two means, the means of two different groups. So a quantitative variable, a numerical variable that can vary from a low value to a high value, and so that individuals can all get scores on it, and you can calculate a mean of a group of individuals, and you have two groups, either two groups of individuals or two groups of observations from the same individual. We'll get into that in a few minutes. So if you have two sample means, you have two groups of observations, and each group or each sample mean from each group is an estimate of some population mean, some mu. As we've talked about before, every time you have a sample statistic, it is automatically an estimate of the population value, the population parameter that it corresponds to. So if you are sampling, then all the values in that sample are estimates of the population that that sample came from. So are both population means equal to each other? Are the population means basically the same value? The null hypothesis is always that they are equal. Now, it is possible to make more interesting null hypotheses than these, but almost nobody does, and it gets complicated for an intro class. So let's just say the null hypothesis is that the sample means are equal to each other. Mu1 equals mu2. The alternative hypothesis is they're not equal. Now, the alternative could also be that that mu1 is greater than mu2 or less than mu2. Saying that they're equal is effectively the same as saying, did both samples come from the same place? Did they come from the same population? That could mean the same group of people or the same process that created these values. And saying that they're different is saying they came from different populations. So we really are talking about differences in where things came from. We're back into this situation of looking at some sample means, some statistics, and saying, where did you come from? Did you come from the same place or did you come from two different places? So the way we do this in math, in stats, we skip over this sometimes, but I want to mention it. We crunch things together. We take multiple numbers and we do math on them, subtraction and dividing and things like that, to turn them into a single number. So mathematically, our hypotheses are always represented this way. The null hypothesis is mu1 minus mu2, equals 0. And the alternative is mu1 minus mu2 is not equal to 0. Now, of course, you could flip mu2 and mu1 around, but that has consequences. It doesn't really make things harder or easier or anything like that. You just have to keep track. You have to remember which one you said was first and which one you said was second. If you're dealing with software, sometimes you have to go to great lengths to figure out which one the software thinks is first, which sample mean the software said was subtracting the other mean, or was it reversed? So of course you can write these this way as well. So if the sample mean is an estimate of the population mean, then we have this kind of a situation in that cloud, that imaginary land. You have a sample, those blocky red dots down there, and then you have that pretty stripy thing. That's the population with all of its many, many, many values. And that mu true is the population's true mean. We use that situation when there's a single a single sample mean. Sometimes we say the true mean. So the sample mean is an estimate of that population mean. And if we had to guess what that population mean was, of course, our best guess would be the sample mean, unless we needed to use robust statistics because of a skew issue, but as long as everything is behaving itself. So if that's the case, then the difference between two sample means is also an estimate of the difference between two population means. And the situation gets one extra complication. So now you have a difference between two sample means. Each of those samples represents a population. So sample 1, x bar 1, or sample mean 1 is the best estimate of mu1, the population mean for group 1, and sample 2 for mu2. And so now we can imagine randomly sampling from each of those populations, lots and lots and lots and lots and lots of times. Lots of samples, and each sample has the same sample size as sample 1 from population 1, and each of those samples gets a mean. And then from population 2, the same thing. Each sample has the same sample size as sample 2, and each one gets a mean calculated the same way as x bar 2. So you have a whole bunch of alternative x bar 1s and alternative x bar 2s. And then you imagine taking them a pair at a time, and always in the same order. So if it's x bar 1 minus x bar 2, you always take something from the purple cloud and subtract from that something from the blue cloud over and over again. A sample from population 1 minus a sample from population 2. Not just a sample, actually, that's the mean. A mean from population 1 minus a mean from population 2. And so we get lots and lots of sample means here. Lots of sample means together, you subtract those, and it's a single value, right? Like 3 minus 2, you get a 1. So all of those means, you subtract them, creating individual single values. And then those single values you imagine as being a new distribution. And that is our sampling distribution. That new distribution is the distribution of all differences between sample means. So go over that logic until it makes sense. Our research question is always going to be, where did our sample mean difference come from? If our sample mean difference is a certain size, where does it fit in the scheme of where all possible sample mean differences might come from if we constructed a distribution of all possible sample mean differences like this? So it's just like the situation for a single sample and imagining the sampling distribution like for a confidence interval or a hypothesis test, except that now instead of dealing with individual values, we're dealing with values that used to be two values. So each value in this distribution is a single value, but it used to be two things. It used to be that and that, but we subtracted them always this way. I mean, if you reverse it, that's okay, but then you always have to do it reversed. You always have to keep track of which one is first and which one is second. And then you have this distribution of all possible differences between sample means. And then we ask ourselves, are those two means really different in the population? So the null hypothesis, of course, is that they are not different. The null hypothesis is always this worst case scenario, straw man, some benchmark that you don't think is true that you want to compare against. And so in this case, the distribution of the null hypothesis is usually very unimaginative. We just think that the mean difference is 0. So that's the same thing as saying in the population, the two populations these things came from, these two sample means came from, are the same population. They have the same values. Therefore, the mean of one is the mean of the other. So the average of one is the average observation of one is the same as the average observation of the other. So there's no point in even saying they're different distributions. They're the same thing. So they're the same place. These two sample means came from the same place. But mathematically, we might say mu1 minus mu2 equals 0. Now, sometimes we write out the difference. We'll do d bar here in a little bit. And sometimes we leave it as mu1 versus mu2, depending on, or mu1 minus mu2, depending on what our needs are at the time. So the shape of that distribution is going to be, as far as we know now, a Z shape. It's basically going to be normal. Each of the populations from which the samples came from is assumed to be normal. Therefore, the differences of all possible values between those populations is also normal. And I'm sure there's a beautiful mathematical proof for that, but just accept it. If both populations were normal, then the sampling distribution of all possible differences between sample means taken from those populations is also normal. The standard deviation of that sampling distribution is the standard error, but it's the standard error of the difference between means. But it's the same thing as any other standard error. It's just the standard deviation of our sampling distribution. But the full name has to include everything that happened there. So it's the standard error of the difference between means. Sometimes we say the standard error of the difference, or sometimes it's so common to do two sample tests, we just say it's the standard error. Context matters. So another way to look at this, here's the situation. You've got some raw scores. Sample 1 is blue, and sample 2 is red. You have two samples. And you got those two samples, and you calculate means for each sample. You got a blue mean and a red mean there. Calculate the difference between those means. You say it's that wide. It's, I don't know, if these are individual units, like 1, 2, 3, 4, 5, 6, I don't know, it's like 15, 20 points wide. If you're really excited, you can count those. So that's the mean between, or that's the difference between those two means. That's how far apart the two means are. Now we imagine to ourselves, where did those two samples come from that gave us those two means? The alternative hypothesis is always that they came from two interestingly different places. So we don't actually ever specify which alternative hypothesis we're talking about, so I'm just going to say this is my alternative hypothesis. That sample 1 came from population 1, which has a mean much, much lower than population 2, and sample 2 came from population 2. So these two samples came from those populations, and those populations are different from each other. That's the alternative hypothesis. Now, that's not what the null hypothesis says. The null hypothesis says, yeah, you got your data, it's the same data, but you got it from two populations that are exactly the same. And it was just random chance that makes it look like they came from two different populations. You just happen to get a few lower values when you thought you were getting the quote-unquote blue sample, and a few higher values when you thought you were getting the quote red sample, unquote. But they all came from the same population. It's just random chance that they happen to look a little bit different from each other. So that's the null hypothesis. Notice the values are the same, and the difference between your sample means is the same, because the null hypothesis and the alternative hypothesis always describe just different possible realities that might have given rise to your data. They don't change your data. Your data is the same. The problem is the data is the same, and we don't know where it came from, the null or the alternative hypothesis, or something that we're not imaginative enough to think of. Now, if this null hypothesis is true, then we can construct our sampling distribution. I'm just doing what I did in the previous animated slide, but just a little bit different conceptualization. So we have this sampling distribution of all possible differences between sample means from sample 1 and sample 2. There you go. Now that sampling distribution is normal as far as we know, if the original two populations were normal. And the standard deviation is the standard error of the difference between the means. So this is our setup here. We've got our raw data, we've got the null or alternative hypothesis in the distribution, the populations of raw data. We don't really know which hypothesis is true, but we assume that the null hypothesis is true for hypothesis testing. And once we do that, then we can say the mean of that sampling distribution of all possible differences between sample means from population 1 and population 2 is 0, because population 1 and population 2 are the same thing. So this is really basically the same thing as just a standard sampling distribution, but we have to think of the complications because there were two samples there. So the procedure is really similar to previous procedures. We specify both hypotheses, null and alternative. We draw and label a graph, a diagram. We find a critical statistic. Now, a computer won't find a critical statistic. It'll just calculate the p-value out to like 25 decimal places. But when we're doing things by hand, it really reduces our workload, and it also helps us conceptualize what's going on a little better to find our critical statistic and then calculate the observed statistic, so the z-score that goes with the actual difference between means versus the z-score that we need to beat for a difference between means. We compare the observed to the critical, we make a decision about the null hypothesis, and then we state our conclusion. So the technical part was the calculation. And this calculation always takes the same form. There's a point estimate. Our observed statistic is a point estimate. Subtract from that the null hypothesis estimate of what that point estimate should be if the null hypothesis were true and totally influencing everything. So we want to see the distance between our sample point estimate and then the expected value of all possible samples in the null hypothesis, right? And divided by standard error. So point estimate minus a null value divided by standard error. That's what the hypothesis tests always look like. That's a standard pattern. So in this case, the point estimate is not going to be a sample mean. It's going to be a difference between two sample means. That's the wrinkle, the complication. It's not a massive paradigm shift, but it's different. The null value is almost always 0, and so it drops out of the equations quickly. And the standard error is the standard error of the sampling distribution, but because the sampling distribution is a distribution of all possible differences, then the standard error has that big, long name. Now, for standard errors, you just find what kind of test you're doing, figure out which one you're supposed to be doing, and then just look up the formula for the standard error. We could go into why it happens, but I don't why it's the right formula, but that seems like a waste of our time in this class. So if you really want to find out, come talk to me, I'll give you some resources. So we have these same kind of questions. I wrote the same list of questions I had for single sample hypothesis tests. So what's the sample point estimate? It's the difference between our two sample means. That's our best estimate of what the difference between the two population means is. What's the sampling distribution? It's the distribution of all possible differences between sample means. So that's the sampling distribution. It's not the sampling distribution of the mean. It's the sampling distribution of differences, or sampling distribution of the difference is kind of how we say it sometimes. So what's the mean of that distribution? It's 0, because the null hypothesis is true in this situation. So we're always assuming the null hypothesis is true, and so the mean of the sampling distribution when the null hypothesis is true is the mean of a distribution crafted from two distributions that were exactly the same, from the differences between them. Well, the difference between something and itself is nothing, and something even with some variability in itself, on average, is nothing. So 0. What's the standard error? Depends on the test, but you just look up the formula. So before we dive into two sample tests, we have to talk about these 3 kinds of data grouping that we might deal with. You have to remember that when we're talking about groups, you have to shift your brain and say we're not talking about groups of people. And in psychology and sociology, we often think that groups are people, but groups are often not people. Groups can be rocks or whatever, cities in the best places data. But also groups can be a little more complex. And so shift your brain to thinking the group isn't the people. The group is the data you got from the people. It's not the rocks, it's the data you got from the rocks. So groups are observations. They're not groups of objects, they're not groups of people. So you can get fooled pretty easily sometimes thinking of this. The simplest data grouping situation, the data setup, data structure, is one group of participants. And we've been dealing with that so far. So you have one group of participants who I represented with these 8 little guys here. And each person or each object or each case gives you one data point. On those data points, you collect them and put them in tables and write them down and make histograms out of them and put them in your software and make confidence intervals for the mean and things like that. So you can calculate a mean from that one group, and you could test it against some null hypothesis value for a mean, for instance, and you can do a Z or a T test that way. With paired data, you have one group of subjects still, but now each subject gives you 2 measurements. And so as a result, you have 2 groups of observations. So you can have 2 groups, but they came from the same group of people. So those same 8 people, but each person gives you 2 observations. So one example would be a study I did where I asked students both their ACT verbal score and their ACT math score. So you could think that group 1 is verbal and group 2 is math. You end up with 2 groups of scores, but there was only one group of people. But you still have 2 groups, 2 sets of information. You don't have one set of information with some complications. You have 2 sets of information. But those 2 sets of information are associated with each other because they came from the same people. Those people link them, and those people mean that the 2 groups have something in common. Now, the third situation is 2 independent groups. And that's when you have 2 groups of subjects, 1 measurement per subject. So you still get 2 groups of observations, but this time it came from 2 separate groups of people. So group 1, I put 8 people over here. Let's say you give the ACT verbal test to just 8 students, and that's their test. And you calculate the mean of the verbal test. And you get 8 different students, and you calculate the ACT quantitative, the ACT math. and then you calculate that. So we're seeing the structure here. If not, go back and talk about it again, read it again, look at it, come talk to me. This is a pretty important thing to get here. You have to understand your data structure before you're able to actually calculate anything. So now flashing forward quickly, there's going to be a number of tests for means, and let's talk about 1 and 2 means. For more than that, we'll do ANOVA later, but for right now, just 1 and 2 means. So there's a number of situations going on here. There's 2 different dimensions to this. Number 1, sometimes we know the standard deviation of the population, and sometimes we don't. As we've seen already, this is more common, not knowing it. And sometimes we're looking at 1 mean or 2 means with paired data or 2 means with independent data. So we have 6 potential combinations there, except that 2 of those never, ever, ever get used. We're never going to use z-tests for 2 groups because we never know the population standard deviation. It's an unrealistic thing. It's possible to do, the tests exist, but nobody ever uses them. We rarely use the one sample z. Just about always we're using these 3 down here, the one sample t-test, the paired samples t-test, and the independent samples t-test. So here's some, I don't know why I have this extra slide here. I have an extra slide that has exactly the same thing as the last slide, but without that silly extra column on it. And I'm out.